In this highlight video, we will discuss two mechanisms by which substitution reactions can take place. They are called SN2 and SN1. After watching this video, you will be able to contrast the SN2 and SN1 reaction mechanisms. You will be able to describe how the alkyl group of the alkyl halide influences which substitution mechanisms take place, and you will be able to identify the methods by which the mechanism can be determined. If we were to think about how a substitution reaction might take place, we might come up with two viable ways. The first might be a single-step mechanism, where the nucleophile directly attacks the alkyl halide, displacing the halide leaving group. This is a concerted mechanism, which means that all of the bond breaking and bond forming take place simultaneously. The second possible mechanism might be the two-step mechanism, where the leaving group leaves from the alkyl halide first, forming a carbocation intermediate, which then reacts with the nucleophile to form the final product. In this two-step mechanism, the first step is purely a bond breaking step, and the second step is a bond forming step. Let's look first at the single-step mechanism. When this mechanism is operative, the rate of the reaction depends upon the concentrations of both the nucleophile and the electrophile. So in this reaction, this acetate will directly attack the carbon, displacing the bromide all in one step. So the rate of this reaction will equal K, the rate constant, times the concentrations of both the nucleophile and the electrophile. And because of this, this reaction is a second-order reaction, because the reaction rate depends upon the concentrations of two species, and we could also call it bimolecular. So that's where the name comes from. SN2 stands for substitution nucleophilic second order or bimolecular. Let's look at what the reaction energy diagram might look like for this reaction. Since it's a single step reaction, there will only be a single transition state. So remember, on these diagrams we have energy along the y-axis, and this is the reaction coordinate along the x-axis. So we would have our reactants here. This would be, this is called acetate, plus bromomethane, and we would have our product over here, which is called methyl acetate. It's an ester plus bromide. In between these two, we're going to have a single transition state. So it's going to go up over that hump and back down to the product. The transition state up here would involve forming the bond and breaking the bonds. So we might draw it out looking something like this. We're going to be forming a bond to the carbon, and we're going to be breaking a bond to the bromide. We notice that in the reactants, the full negative charge is on the oxygen. It's giving away electrons, so in the transition state, it would have a delta minus. And the bromide is neutral in the reactants, but it has a minus charge in the products, so it's developing a minus charge as the reaction progresses. So this is how we might draw the transition state. In contrast, the two-step mechanism, the rate of the reaction is only dependent on the concentration of the alkyl halide. So it's also the rate equals the rate constant, but in this case it's only times the concentration of the alkyl halide. Notice that the nucleophile does not show up in the rate expression or the rate law. No nucleophile here. So this tells us that the nucleophile is not part of the rate determining step. So let's draw out what the rate, or not the rate, the reaction energy diagram would look for this reaction mechanism. So we have the reaction coordinate here and the energy up here. Again, we're going to have the reactants, the reactants and the final product looking about the same. And so here is our nucleophile and our alkyl halide. But in this case, because this is a two-step reaction, we're going to also have an intermediate. Let's go ahead and draw out the whole mechanism. So we're going to start with the alkyl halide, and like we showed before, the first step of this mechanism involves simply loss of the leaving group. This generates a carbocation intermediate plus the leaving group. In the second step, that carbocation reacts with the nucleophile, where we have the minus charge reacting with the plus charge, and this generates our final product. All right, between these two steps, we know that the first step is bond breaking only, so that's going to take more energy. So this is going to be the slow step. This is going to be the fast step. So when we draw our reaction coordinate diagram, we know we're going to have the intermediate. This is going to be the carbocation intermediate. The first step is the rate determining step. It has the highest energy transition state. And the second step is the fast step. And over here we have our product like this. If we were going to draw out both of the transition states, or what the transition states might look like for this reaction, we could say transition state 1, that would be right here, is going to be only losing the bromide. So this bond is going to be breaking. And as that bond breaks, it's going to be developing a minus charge onto the bromine and a plus charge onto the carbon. Transition state 2 is kind of just the opposite. That in this case, we're going to have this carbocation that is reacting with the oxygen. We're going to have only a delta plus on the carbon and a delta minus on the oxygen. So we have these two mechanisms, the one-step and the two-step mechanism. How would we tell for a given reaction which of these mechanisms were taking place? Well, the first hint, or the first way that we could do this, comes from the two different rate laws. So notice that in the one-step reaction mechanism, the rate includes both reactants, the nucleophile and the electrophile. And in the SN1 mechanism, the rate law only includes the halide, or the electrophile. So if we vary the concentration of the nucleophile, the reaction rate should only increase or change when we have the one-step mechanism. Because the nucleophile does not appear in the rate law for the two-step mechanism, varying the concentration of the nucleophile should have no effect on this rate. So we vary this if the rate changes, then it would have to be an SN2 mechanism. For some substrates, particularly those where the leaving group is attached directly to a stereogenic center, we can use stereochemistry as another way to determine which mechanism is operative. For the SN2 mechanism, we might imagine two different ways that the nucleophile could approach the alkyl halide. One way would be for the nucleophile to approach from the same side as the leaving group. That would be having it come around to the same side as the leaving group. If we did this, or if this took place, we would get a product where the configuration, or the R or S, remains the same. So we would call this a retention of configuration. So if we start with R, we should get R. If we start with S, we should get S, as long as the nucleophile, the product, has the same order of priorities for determining R or S. The other way that this reaction could take place would be with the nucleophile attacking from the side opposite of the leaving group. If this happens, we go through a transition state where we have the nucleophile attacking here, the bromide attacking on the other side, and as the bromide comes off, the stereochemistry inverts. So this mode would include the inversion of configuration. The configuration is just whether it's R or S. Notice that this product here and this product here, what's the relationship between these two? Okay, these two are in fact enantiomers. All right? And if we were to run this experiment, what we would find, if the SN2 mechanism is operative, we always get inversion of configuration. For the SN1 mechanism, because the first step involves loss of this leaving group to form this carbocation, and remember carbocations are just planar, the nucleophile can come either in from the top or it can come in from the bottom. And this gives us two different products. Here's the nucleophile on top with a wedged bond. Here's the nucleophile on the back. These two, what's the relationship between these two? These are enantiomers. and they are formed in equal amounts. So this is a racemic mixture. It means a 1-to-1 mixture of R and S, or a mixture of enantiomers. So if we have a substrate that has the leaving group attached directly to a stereogenic center, if we run a substitution reaction and we get inversion of configuration, we know that an SN2 mechanism took place. If we lose the stereochemistry, or we get a racemic mixture, then we know that the SN1 mechanism was operative. The component of the substitution reaction that we haven't talked about yet is the structure of the R group that's part of the alkyl halide. So let's compare whether we have a methyl group attached to the halide, or that position is primary, secondary, or tertiary. Remember these terms. Primary, for example, means that the carbon attached to the halide is bonded to a single carbon. Secondary means that that carbon that's bonded to the halide is bonded to 2 carbons, and so on. If we were to run these reactions, what we would find is that from primary and methyl, we only observe SN2 mechanisms. For tertiary, we only observe SN1 mechanisms. And for secondary, we can observe SN2 or SN1 mechanisms. All right, so there's a definite preference for mechanism based upon the substitution pattern of the R group. So why would this be? There are 2 main factors. The first has to do with steric strain. So if we compare these alkyl groups, so here we have the methyl, here we have primary, this is secondary, and this is tertiary. We know now that for an SN2 substitution, the nucleophile is going to approach from the side opposite the leaving group. So if we compare how this nucleophile has access to this carbon for a methyl halide compared to how that nucleophile has access to the carbon for the tertiary alkyl halide, we would notice that over here, this is starting to get very crowded, and it's difficult for the nucleophile to access the carbon to carry out the substitution reaction. So, as we increase the branching or bulk of the alkyl group, it is going to disfavor the SN2 reaction. So we go this direction, we disfavor SN2, so we're going to favor SN2 going the other direction. So methyl and primary are favored for SN2, tertiary is very much disfavored. The second thing that plays a role here is the stability of the intermediate. Remember, we form a carbocation as the intermediate in the SN1 mechanism. So we need to understand, as we go from methyl to primary to secondary to tertiary carbocations, how does this substitution affect the stability? What we find is that the stability of the carbocation increases as we add more alkyl groups. Okay, so why would this be? Let's start out by thinking about what would stabilize a carbocation. We saw when we were talking about acid-base chemistry that if we have an anion for example, in a conjugate base, the way that we could stabilize that anion is to withdraw electron density away from the anion. For a carbocation, it will be just the opposite. Carbocations are stabilized by electron donating groups. Let's write this down here. I'll say carbocations, but this is really true for all cations, are stabilized by electron donating groups. Okay, so what does that tell us then about these R groups? If we add one R group, it gets more stable. If we add two, more stable. If we add three of them, it's even more stable. So what this tells us is that the alkyl groups can act as electron donating groups. So if we imagine, here's the carbocation, here's a carbon with different bonds. These carbon bonds, or the electrons around the substituent, are able to donate electron density to the carbocation. And the more of those groups we have donating electron density, the more stable is the carbocation. So, why does having a more stable carbocation increase the rate of the reaction? Or why does that favor the SN1 mechanism? So if we go this direction, this is going to favor the SN1, so it must mean that the carbocation forms faster, because we're increasing the rate of SN1. So, can we make the direct comparison between the stability of the intermediate and the rate by which it's formed? So this is kind of an issue, because by combining those two issues, we are mixing together kinetics, which is the rate, and thermodynamics, which involves the stability, and we're really not supposed to mix those two together. So we can mix them together, though, based upon something that's called the Hammond postulate. So look that up, and we're going to talk about it a little bit later when we apply it to the reactions of alkenes.